Okay, hello everyone. I'm İlke Demir. Currently, I'm a postdoc at Facebook. Thanks, Chris, for the introduction. And now we know how to explain models, thanks to Bean, and now we know where the data comes from, thanks to Gopal. We will talk about how we can actually use geospatial machine learning for understanding the world and changing the world. So those are the two main topics that we will talk about today. So we will talk about land, streets, roads, urban score, data, images, imagery, DeepGlobe, approaches, dataset, SpaceNet. We will talk about all of these. So just like as a overall ideas and overall keywords that we will talk about. So yeah, we need to cover all of them fast. But looking to the motivation of those, covering the motivation of understanding the world, why? So why do we need to like discover or classify the roads and settlements and land types and landmarks and addresses? Why there is this recent proliferation of remote sensing data to better understand our world? Cool. So it affects our lives, and understanding the world connects us and defies distance and enables service, and in a sense it equates us, it frees us. Like we can be everywhere and we can be informed about everything, and we can just like depend on data for such things, for reaching out, for being free of distances. So with the recent advancements in deep learning, we can actually understand the world using even more complex models. So we can just look at street view images and comprehend the safety areas. For example, like what is, if looking just street view images, is this street a safe place? Or assigning safety scores for having better understanding of urban safety. We can locate, analyze, and maybe prevent disasters by just looking at satellite images and by just like looking, developing deep learning models for crises that happened before. We can better model poverty. We can see with data where we are blinded by biases. We can develop models just like understanding where people are living with which levels of like production or etc. We can even like look at cars, just like look at cars and cars and street images, of course, to develop a model of spatial socioeconomic data, which can be further used for extracting voting patterns, which is like an understanding the world and understanding the humans. And we can just do all of those by like deep learning and like just like looking at small representative sets over our data. So it all builds a picture, right? Like it all gives an idea of like understanding the world, understanding us, and understanding humans. So how? We have all those like ideas. We have all those like great motivation of understanding the world, but how? So these are currently open. There are many open data sets right now. These are just the ones that me and some of my close colleagues are being a part of. So the first one that I will also talk about later is DeepGlobe. It includes like 3 data sets for road extraction, building detection, and land cover classification. The other one is SpaceNet. It used to have the previous version has road network extraction, and the current one has building detection with much better imagery and much better annotations. The other one is Earth Observation Challenge by DigitalGlobe, I guess. And the challenge has 2 parts. One is water resource extraction, and the other one is change detection. To understand like more how the world is actually evolving. The other one is data fusion contest, which is land cover, land use classification from various sensor data. So it's not just images, but like we have LiDARs and etc. And the last one that I will talk about is functional map of the world, which is labeling the world into land use categories about like buildings, facilities, etc. So let's focus on DeepGlobe, and I will explain how a challenge from beginning to end works and what we found and how our data sets are still being used. So DeepGlobe is a satellite image understanding challenge that took place in CVPR this year. DeepGlobe contains 3 data sets structured for solving 3 different satellite image understanding tasks. It organizes utilizes these data sets for public challenges to propose solution to these tasks that I mentioned before. And it gathers these urges from diverse fields to collaborate on those different things. So the data sets are created and released for this competition also serves as a benchmark for other tasks and other challenges, such as like disaster. I just recently found out that a paper is using our data sets for crisis recovery and like finding from satellite images like how we can actually map, detect the crisis areas. So going into details of DeepGlobe, DeepGlobe had a road extraction challenge. So in disaster zones, especially in developing countries, maps and accessibility information are really crucial. And we posed the challenge of automatically extracting roads and street networks remotely from satellite images as the first step for automated crisis response and increased map coverage for connectivity. Building detection challenge. So as evident by recent natural events, modeling population dynamics is of great importance for disaster response and recovery. So modeling urban demographics is a vital task, and detection of buildings and urban areas are key to achieve this. So we pose the challenge of automatically detecting buildings from satellite imagery for gathering aggregate urban information remotely, as well as gathering detailed information about spatial distribution of urban settlements. And the last one is land cover classification. So automatic categorization and segmentation of land cover is essential for sustainable development, architecture, forestry, and urban planning. So we pose a challenge of classifying land types from satellite images for economic and agricultural automation solutions. So what happened? Road extraction challenge includes digital globe imagery with high resolution, and it is annotated pixel-wise by our annotators in 2 classes, which is road and non-road. It included Thailand, Indonesia, and India, and it included like 8,000 images, and we split it for test training sets. And as you can see in the image, we had like diverse road networks. So it's not always like European like grid-like structures. And in the DeepGlobe Road Extraction Challenge, we had over 300 participants with 2,000 submissions and many results. This is as of June 2018. And if you look at our results in dashboard, like it's over 100. And like we still, even the challenge ended, we still keep getting many participants and many requests for the dataset use, and we have many other results in the leaderboard. The same is valid for building detection too. So building detection used SpaceNet Buildings version 2 dataset. Just to mention again, now they have a new one, Buildings version 3, which with more imagery. These are the dataset stats. You can find them online. And again, we had like 300 participants with many submissions. And these are, I think we have even more, like 40 results in leaderboard right now. And that DeepGlobe Land Cover Classification Challenge, again, like digital globe imagery with 50 centimeter resolution and with 7 classes. So this is not a binary classification problem, but this is a multi-class classification problem with urban, agricultural, rangeland, forest, water, etc. And again, I think this data set is being used for other purposes than land cover classification right now, because we keep seeing that there are the increase in the leaderboard for DeepGlobe land cover classification is much more than the others. So those are the results and baselines. For roads, we use a deep lab variation for finding and extracting the roads. We did the data augmentation by rotation, and we reached an IOU score of 0.545. For buildings, the best result by that time F1 score of 0.69. And the lens, we again used another deep lab variation, and we reached a score of 0.4, which are much more, so these results are the baselines, but the actual results have improved those by a good range, good gap. So which are those approaches, right? Here you can see the DeepGlobe winners with roads for D-link net. Buildings are using an ensemble of specific size-specific detectors, and for lands, there is a dense fusion classmate network, which is a novel network architecture. And the others are all papers that I will link at the end of the presentation. So now we know how to understand the world. Like, at least we have resources, we have the data sets, we have the ideas why we are doing it. So now let's change the world, right? So generative approaches in general leverage existing data models to digitize the world, to create new worlds, to develop new schemes that can explain the world in a better sense, that we can, if we want to expand our world, we can use those approaches. So those are used in urban planning simulations, for example. If you can base your generative model modeling San Francisco, then maybe you can just like change some sliders to increase interior light or decrease carbon dioxide emission or something else to find a new version of San Francisco in 5 years. Maybe that's the new urban plan that we should do, etc. And the one on the right shows a generative model for creating maps. So for areas that doesn't have any maps, doesn't have any indicators, but just streets, how can we actually model generative models for just by looking at satellite images, how can we actually find maps, find street addresses that can explain those places? So these generative models, or let's say procedural models, or creation models, enable users to efficiently, interactively, and creatively generate new content. And they also have real-world assistance and potential to change the world, because you are not just looking at the images, you are not just analyzing the images, but you are actually creating and devising new schemes to create and generate new content. In 3D shape understanding and 3D modeling, this is proceduralization, which is getting the real-world data. This can be images, 3D models, point clouds, meshes, whatever you have, whatever data you have of the 3D actual real world. Then you process it with this pipeline to create a procedural world or a generative scheme or a representation that actually can explain and represent efficiently the real world. So as you see in the pipeline, there are like 2 parts, which is shape understanding and then grammar discovery. So shape understanding, we propose different solutions for segmentation and labeling, which is shape understanding part of the proceduralization framework. You can apply it to point clouds to find the units that can represent the point cloud. You can apply it to physical objects that you can find the units of repetition or units of expressive content. You can apply it to urban spaces that you can maybe understand and cluster all of the buildings in an urban space to create more models like that. You can apply it to satellite images to find the road networks and then create generative models on top of those satellite images. And you can also apply it to architectural models to find the units of repetition or how this real-world architectural model was actually built and how we can actually replicate some of the interesting style decisions. And of course, after you have those units of repetitions, you can use that shape understanding for creating more models. For point clouds, you can have a point cloud. We proposed a point cloud editor based on the procedural representation that we proposed for understanding point clouds. For satellite images, I will go into more detail. For urban spaces, this is a model of New York City, for example, and there are like 4,000 buildings in New York normally, but this almost realistic representation of New York was just modeled by 200 buildings, which is like compression, expressivity, style decisions, even the neighborhood information of like office buildings or residential buildings or whatever neighborhood information that you have is actually preserved in that procedurally generated representation. Even for architecture, you can take existing 3D meshes, 3D point clouds of like Stamford Square or Cinderella's Castle or Blue Mosque with any architectural design decisions, and you can replicate and model new ones based on whatever representation you actually extracted from the original model or original real-world data. So let's look at one of those cases, which is in line with what Gopal just explained us. So we can use satellite imagery and those analysis to have a generative model for creating maps, creating satellite images. So why do we need street addresses, right? Like we all have addresses. Why do we need to create them? Actually, that's not true for the whole world. And 75% of the streets of the world doesn't have adequate addressing. According to UN, 4 billion people are invisible because of that. They lack services, they lack basic needs, they lack, like you just have that huge paragraph that explains your address, but there is no, I don't know, 19 Mason Street, etc. And of course, there are many initiatives like OpenStreetMap and HatOSM, etc., for such initiatives in disaster response and crisis response. But still, doing this remotely is a much stronger motivation. And talking about naming things, of course, like just like say latitude, longitude, right? Like why do we even need the addresses? So, the current geocoding solutions actually focus on naming just based on latitude, longitude. So you have a function of that, and that's called address. That can be like 3 random words, that can be your favorite tag, that can be a hash that is based on that, but that doesn't give any information about any special queue. So your address is completely different from your neighbor's address. Or you cannot do self-localization, or there is no city, state, country information. You can just like, instead of saying parrot, you can say parrots, and you are suddenly not in New Zealand, but you are in Africa, or etc., right? And there's no accessibility information. If I give you latitude, longitude, you have no idea about going one to other one. You can just like, you cannot just Euclidean distance walk, right? You need streets for accessibility. And humans need streets to express their relative positions just because of this information. So we don't need, on the bright side, we don't need to reinvent addresses, right? There are many addresses in the world, so we can get inspirations. There are many addressing schemes that are already organically being developed and experimented throughout the history, we looked at them. And for example, Dubai addressing system uses districts. Berlin uses zigzag house numbering pattern. There are meter markers in the literature, and there are like block systems that you take blocks instead of going along the streets. And excuse me. There is also a London postal code system, which has radial regions based on orientation and distance. So we looked all of those, and London postal code system caught our attention with its linear and hierarchical features. So what it explains is you have a downtown, and if you are north of the downtown, then the region is N. If you are west of the downtown, then your region is W. And the numbering expresses your distance from the downtown. So based on those, we developed our generative addressing scheme. So it consists of 5 alphanumeric fields, hierarchically designated larger areas in order. It resembles real-world addresses. So if you have an address like 17 Hacker Way, Menlo Park, it looks something like 75A and NK42 Menlo, CA, US. And the last field is left for versioning. So the region naming scheme is inspired from the London scheme, as in the previous slide. And the first letter is dedicated for orientation from the downtown, so north, south, west, east. And this little yellow house here has west, because it's in the west of the downtown. For the road naming scheme, we name all the regions based on their orientation. So if it's like north-south, it is odd, and if it's like west-east, it is it's even. Then we order them based on their distance. So that brings me to the last one, which is the distance fields along the streets, which are, for example, here, again, the meter marking concept, 32, and 32 along the street, and K units from the street. So at the end, the name of that little house becomes 32K NK21, sorry, WK21. So that's like the house cell and the street name of the street. So how do we do that? We looked at satellite images, and of course, like for especially for developing countries, the urban structure in those areas are not easy to detect or organize. So we developed our deep learning model based on SegNet, and later we improved it with a DeepGlobe model, and we have the road predictions. Then from the road predictions, we derive the road segments by orientation bucketing and median filtering. Then we convert those to road networks. And from road networks, we use graph partitioning to find regions that represent the neighborhood information that is geographically plausible. If there's a river, then of course river cuts two regions, and there are like separate regions, etc. So it is like geographically and human-wise interpretable. Then we name them based on their orientation. We again do orientation bucketing based on the downtown, then north, south, west, east, and then we trace the regions, and we name the roads based on the regions and their orientation. Then we come to address cells. We just define distance fields based on the streets. So 5 meters along the street, and then odd even based on which side of the road you are, and that gives you the address cells. So this is one result from satellite imagery to extracted roads, to named roads, and to distance fields. So as defined in our motivation, we want to locate and connect the invisible 4 billion, right? We tested our system on unmapped developing countries like this, and the map coverage improved up to 80% in some areas, and we processed more than 200 districts, and that's increasing. Road network is being discovered in non-urban settings too, which is a step for changing the world, I guess. So now that we have many ideas, now we know how to understand the world, now we have ideas about changing the world, and here's how you can share those ideas. So news and ads for Eminence. To begin with, we currently have a spatial issue on geospatial modeling and visualization in Big Earth Data Journal, and I'm the editor of that. So if you have any papers, we are waiting for that. There's another challenge, which is understanding not outdoor scenes, but indoor scenes from 360 RGBD images, which is called Sumo challenge, and we are currently accepting accepting submissions about understanding, this is like 3D scene understanding, so we have meshes, voxels, and bounding boxes as tracks. There's also the special session for deep learning in remote sensing in Living Planet Symposium. We will also have more detailed presentation in ML4D workshop in NIPS 2018. This year, either me or my postdoc advisor, Ramesh Askar, will give the talk. We have Earth Vision 2019, which is a great workshop for collaboration and all of those opportunities to be shared. And hopefully, one day we will have DeepGlobe version 2, which we have requests, and probably it will include like temporal data or small object detection or more tasks to be included. So this is all for me. Thank you. These are all the links for generative street addresses. Our code is online. Our paper is online. For DeepGlobe, the dataset is still open. We are getting submissions per minute. Papers are online. Workshop papers are online. Website is there. My information is there. And I would like to conclude with thanking all my colleagues in Facebook, in Purdue, and everywhere that are that have many valuable work on both of these projects and all the other projects that I mentioned. Thank you.